Okay. Yes, so I'm going to talk about the Assimilation of ATMS, which is a microwave sounding instrument on the American satellites Suomi-NPP and NOAA-20. So the first half of my talk will be on data quality assessment of the newly launched NOAA-20 instrument, and then I'll also talk about accounting for correlated errors in the second half. So a couple of points just to mention how we pre-process the ATMS data that we use. Firstly, we do a 3x3 averaging because the instrument fields of view are oversampled, and this makes the data characteristics more similar to the legacy instrument AMSU-A in terms of spatial resolution and noise. We are only assimilating this in clear skies at the moment, so we run a clear sky radiative transfer model. And we retrieve emissivity over land and sea ice. And then we use quality control, including cloud screening, based on window channel first guess departures. So the first thing to do is to compare the global first guess departure statistics for NOAA-20 against the existing Suomi-NPP ATMS. So this plot shows in the solid lines the biases, in red Suomi-NPP, in blue NOAA-20. So the first thing to note is that the biases are slightly larger for NOAA-20, and as in slightly further away from zero, but they're not too dissimilar, and our bias correction is pretty well able to correct for these. The other thing to say is the dashed lines are the standard deviations, and you can see that the blue line for NOAA-20 is significantly lower than the red line, and this is always good. We always like to see smaller standard deviations of first guess departures because it means the data quality is really good. Another way to visualize that is on the right, the black line is the normalized Suomi-NPP values, and then the blue line is the equivalent NOAA-20 values, showing that we have between 15 and 20% reductions in the standard deviations of first guess departures, and that's due to lower instrument noise on the newer instrument. The next thing to look at is the scan-dependent biases. So this is basically showing the instrument is scanning in a cross-track direction, and so on the left is the edge of the scan, in the middle is at nadir, and on the right is the other edge of the scan. And on the left here is NOAA-20, on the right is Suomi-NPP, and we can see that again the biases are slightly larger, slightly further away from zero for NOAA-20, but in terms of the structure of the biases they look quite similar. They're kind of similarly symmetric and a similar shape, and our bias correction is a third order polynomial, so it can deal with this quite nicely. The top is for the temperature sounding channels, and these are for the humidity sounding channels. So again, the story is quite similar. So one thing that we experienced with the first ATMS was striping in the first guess maps of first guess departures and correlated instrument noise, and this is caused by a low noise amplifier on the instrument, which introduces a 1/f component to the instrument noise. So I looked at the diagnosed interchannel correlations for NOAA-20 on the left and Suomi-NPP on the right, and you can see that the correlations, particularly in the temperature sounding channels in the top left, are significantly weaker for NOAA-20. So this suggested that this issue is slightly less dominant for NOAA-20 than it is for Suomi-NPP. You can also look at maps, although it's quite hard to see. So on the left is NOAA-20, on the right is Suomi-NPP, and if you look kind of close enough, you can sort of see that there's a striping signal that is possibly slightly weaker on the right than it is on the left. But a better way to look at this is to look at the ratio of the unaveraged versus the 3x3 averaged instrument noise. So in a perfectly Gaussian noise case, this should be equal to 3, which is shown by the black line. The blue line shows Suomi-NPP, and the green line shows NOAA-20. So you can see that NOAA-20 is definitely closer to 3 for most channels, which is again a good thing. So moving on to some assimilation experiments using this data on top of our existing system. So one of the first things we look at is the change in first guess fits to independent observations that we haven't changed, and generally we want to see a reduction in the standard deviation of first guess departures. So on these plots, the black straight 100% line is the control, and then anything to the left of that is showing an improved fit, which is indicating an improved short-range forecast. Anything to the right is a degradation. And so you can see for temperature observations, we generally see that everything, or nearly everything, is to the left of the line, showing improved temperature forecast, short-range temperature forecasts throughout the atmosphere. And this is also the case for humidity-sensitive observations. So here I've shown MHS, but it's also the case for geostationary clear sky radiances and other observation types as well. And then also looking at the longer-range forecast scores. So this is showing the change in RMSE of geopotential height forecasts at days 1 to 4. And you can see that blue is generally an improvement on the control, and yellows and reds are a degradation. And you can see that in the stratosphere particularly, we see improved forecasts at kind of short range, but some of those impacts go out to 4 days. And so based on these results, we started assimilating the NOAA-20 ATMS data from May last year, which was about 6 months after launch. And I believe we were the first centre to do that. So that was quite nice. So moving on to the second part of my talk. So this is looking at correlated errors. Initially, just looking at Suomi-NPP because of this striping issue and correlated instrument noise. So when we initially introduced the data, we knew that these errors existed, but at the time we weren't able to actually directly account for the this correlated instrument noise. So what we did is we inflated the errors. So the blue solid line is the assumed observation errors for ATMS, and the blue dashed line are the standard deviation of first guess departures. So you see there's quite a big gap between those two lines. For comparison, the red lines are the equivalent values for METOP B. So you can see that the assumed errors are a lot closer to the standard deviation of first guess departures, and that's where we wanted to get to for ATMS. But to do that, we have to take account of the correlations, otherwise we can overweight the data. So this is a instrument noise correlation matrix, which was provided to me by Vince Leslie at MIT. And you can see that in the top left, we've got a block of strongly correlated channels. So that's the tropospheric temperature sounding channels. In the bottom right, we've got the humidity sounding channels, which often show quite strong correlations from representation errors. So since we initially introduced this data, we've seen quite significant forecast improvements at various different centres by accounting for correlated errors directly, mainly for the infrared instruments, but also Bill Campbell's done this at NRL for ATMS. So what we can do is then we can diagnose the error standard deviations here on the left and the correlations using these methods, Hollingsworth, Lomberg, and de Rosier. And then we can then feed that into our assimilation system and take account of these correlated errors explicitly. So the results, one thing I should say is we generally find that we have to inflate the error diagonal to get improved results. So I tested various different inflation factors and found that inflated by 1.75 gave optimal results. And again, looking at the change in first guess fits here to temperature observations, AMSU-A and GPS-RO, again, the lines are generally to the left, showing improvements, particularly in the troposphere, which is the bottom of the AMSU-A plot there. But also we see improved fits to the humidity-sensitive observations. This is all-sky SSMIS, which is sensitive to cloud, and wind observations. And we also see quite significant improvements in our forecast scores. So on the top is the vector wind in the extratropics. The 0 line is the control, and anything below the line is showing an improvement. So we see improvements of kind of 0.5%, which is significant out to day 3. And on the bottom is geopotential height, and here we see kind of improvements of up to 0.5% to 1%, again with significance out to about day 3. And it's quite rare to see these kind of significant impacts with satellite changes, so that was quite nice to see. And so this will go operational in mid-2019, around June, I think. So the final topic I'm going to talk about is probably the most interesting bit. So this is extending the use of correlated errors to the new NOAA-20 ATMS as well. And as I showed previously, the correlations are weaker, but there's still some significant correlations which we think we can gain benefit from taking account of. So the initial results using the same strategy as I used for Suomi-NPP actually showed some issues, which I'll go into on this slide. So on this plot, this is showing the change in RMSE of the vector wind forecasts when we introduced the NOAA-20 correlated errors on top of the previous system, which had the Suomi-NPP correlated errors. And you see these red areas around the tropopause, around 100 hectopascals at T+12. And this is indicating increased increments in that area of the atmosphere. And generally, in isolation, we might not be too concerned about this because obviously we can see that impact doesn't really last into the forecast. But actually, we also see there are some degradations in the tropics and the northern high latitudes. And additionally, when we look at the first guess fits, we actually see that one of the channels, channel 8, which is sensitive around 100 hectopascals, is showing a degraded fit as well. So we were wondering what was potentially causing this. So this led me to look at the Eigen decomposition of the matrix. So this is showing on the left is the leading eigenvector, and on the right is the trailing eigenvector. So basically on the left, you've got an eigenvector where the contributions are all coming from the humidity sounding channels, and this is potentially a cloud error, which actually we'd probably quite like to downweight given we're assimilating these observations in clear skies. So that's a good thing. On the right, we see this kind of harmonic structure, which Alan was also seeing in the EASI humidity sounding channels, but these are for the tropospheric temperature sounding channels. And it doesn't look like a very realistic picture where you've got neighboring channels with completely opposite signs. So what happens when you use the matrix is because these are the trailing eigenvectors in the R matrix, when you then invert the matrix, you're giving these departures that map onto these modes a much higher weight. And our hypothesis was that this is causing us difficulties where we've got important areas of the atmosphere where the vertical structure is important. So, for instance, around the tropopause. So what we can do is, similar to what Jemima spoke about yesterday, we can then inflate these smallest eigenvalues. So we're then downweighting these modes and then reconstruct the matrix. So yeah, in the blue is the original eigenvalues, and in green is the adjusted eigenvalues. And so this then gives less weight to these modes. It also improves the condition number as a byproduct, although that's not our main motivation here. And the other thing it does is it actually quite significantly weakens the correlations, which you might think, okay, the whole point of us doing this is to add the correlations in, so we might be actually destroying quite a lot of the benefit. But interestingly, when I go to the next slide, when I look at the results using these reconditioned matrices, it's not quite as simple as just destroying all the impact. So the first plot I'm going to show is, again, the change in first guess fits to AMSU-A. So if you just look at channel 8, in black is using the original matrices, in red is using a new matrix. So that's actually definitely improved things for that channel. However, for the other channels, it looks like it's done exactly what I said. It's kind of destroyed all of the positive impact that we got with the original matrices. But then when we look at the forecast scores, so this is what the forecast scores looked like before for the change in vector wind. Again, blue is an improvement, red is worse. And then using the new matrices, so if I kind of flick between those, you can see that using the new matrices introduces a lot more blue, particularly in the southern hemisphere. So it appears that this change is actually a really good thing to do. And this is consistent with what Alan's found with the all-sky microwave images, that these lower eigenvalue modes are actually causing us some degradations. And so thanks to these results, this is now planned for implementation at the next model upgrade. So conclusions, on NOAA-20 ATMS, the data is very good quality compared to Suomi-NPP, with lower and less correlated noise. And the assimilation experiments lead to improved forecasts of various different variables, particularly in stratosphere. And then taking account of ATMS correlated errors, yeah, these can be taken account of directly now. The results showing significant improvements to short-range forecasts and medium-range wind and geopotential forecasts. And then finally, when I added the NOAA-20 correlations, they initially showed degradations, but these were improved by reconditioning the matrices. So that's all I have. Thanks for listening.
Thank you, Peter. Perfect timing.